Good morning, or afternoon, or evening, or middle of the night, whatever it happens to be. Make it good. So velocity in a velocity we're looking at now. Okay, so basically we are looking at how velocities combine if one velocity is within something else that's moving, if that makes sense. We're combining reference frames, and we're going to look at the lingo, the language, how to communicate it, how to work with it. And we'll answer questions like these will make more sense in a minute here. Maybe I won't even talk about that yet because, yeah, once we get to the river question, well, that'll make a lot more sense and it's in the lesson. So, what I will start with is looking at how vectors, velocities, and any vector really, but can be treated as these two separate components and how it helps us analyze situations. So think about a rectangular room that's 12 by 4 meters, and you're going to walk diagonally across it with a velocity of 5 meters per second, right? If I shouldn't even really have given you that number, to be honest. But yeah, this is the situation, and so the questions are: what's your horizontal component of your velocity? What's your vertical component of velocity? Could have asked those later, I suppose, but you'll need these to determine these questions, answers to these questions, right? So how long does it take to walk diagonally across the room? How long does it take to travel the 12-meter length? So basically the idea is going to be to look at the 12-meter length and the velocity in that 12-meter direction, how long that takes, and then how long it takes to travel the 4-meter width. So again, 4-meter width and the velocity in that direction, and we'll see that everything makes sense basically. So in the vertical direction, we have a vertical displacement, and what you're going to see is that we can think of it as being traveled by this vertical velocity. It depends only on that vertical velocity. So you have this velocity equation where we have the vertical velocity equals the vertical displacement divided by the time. And the same thing for the horizontal. That horizontal displacement, the distance or the displacement and the time and the velocity related to each other are just the horizontal components. So how long it takes you to travel horizontally depends only on your horizontal velocity. And then the combined overall actual vector, velocity vector, that actual resulting diagonal displacement depends on that actual velocity vector. So that's the moral of the story from all of this, what we're going to get out of all this. So, first thing you might have to do is calculate some things, right? So obviously we can get the total displacement using the Pythagorean theorem. So that's where that 12.6 number comes from. And the angle, you can just say, okay, well, you got opposite over adjacent, right? 4 over 12. And so really we're talking about tan inverse of the 4 over 12. Physicists tend to jump right to that. Obviously, we could have started with delta D equals, so we'll do this here, delta D squared equals the 12, or the 4 squared plus the 12 squared. And then you take the root of both sides and you end up with this, right? You end up with delta D equals this. Whatever. Big sloppy arrow here. And same thing for the tan inverse thing. We could have said tan of theta equals opposite over hypotenuse, so 4 over 12. Right? And then did tan inverse of both sides. Oops, tan inverse of both sides. And let me just redo that. But yeah, tan inverse of both sides. And of course, that would lead directly to this. Right? I like it better without, to be honest. So I might change that to be green. It's like optional, basically. Physicists skip that stuff, that preliminary stuff. Okay, the black black writing is all you really need if you understand what you're doing, right? So we can get our x component of our velocity. Notice the angle we solved for here is that theta, that 18.4, and so we're looking at the adjacent side, and so it's just going to be the 5 times the cos of the 18.4. Adjacent is cos, right, for components. The vertical component, it's written here, but I mean it could also put a red arrow there too. If I were to shrink the angle down, 1 second here, please. All right, and back. So we have the x component of the velocity there, and then the y component is based on the opposite inside 4. And so we've got 5 times the, oh, sorry, the 4 is the answer, I should say, or whatever. No, the 4. Oh, it's the component. I apologize. I went and did other stuff, and I came back, and I'm rusty here. But yeah, it's the component of the 5, right? So opposite the 18.4 degrees, 5 times sine of 18.4. So we have the horizontal velocity, the green one, the 4.74, and the vertical, the red one, the 1.58. Okay. So in C, how long does it travel diagonally across the room? That's just the 5 meters per second, and the displacement of the 12.6, just directly calculated, giving you 2.5. How long does it take to travel the horizontal displacement based on the horizontal velocity? Also gives you 2.5. And then the vertical, how long does it take to travel the vertical distance based on your vertical velocity? Also gives you 2.5, of course, right? So what we see from this is this all makes sense. Your x components and y components can be treated separately, and everything makes sense. If you've got different times, that'd be a big problem. It would obviously show there's a mistake made, but certainly it doesn't match reality. So the thinking of velocities, vectors separately in xy components. Right, so we can think of them separately, and it'll help us analyze a situation where we look at a velocity in a velocity. And so you can think of a situation where you're in a boat crossing a river. You got the boat's velocity and the river's velocity combining. Or an airplane flying in the wind. You got the plane's velocity and the wind's velocity. Or any situation where you have 2 velocities combining. One of the examples in the homework is like someone walking on a train, right? The train's velocity and your velocity walking inside the train would combine. So here's a visual for us of a boat and a boat in a river kind of question. And so we've got it set up in the program here where we're going to have the boat speed is going to be at a 90-degree angle. So in other words, directly north. That's the way it's pointing. It's going to be traveling at 6 meters per second. The river's speed, so the log floating by there, is 3 meters per second. And so if I click launch boat, you can see that even though it's aiming straight across the river, it's actually getting swept diagonally downstream. So that tiny little thing is the boat, apparently. Okay. So we could actually reset this and look at times later on as a to confirm the numbers, I suppose, or we can do it right now. I didn't stop it when it got to the other side. So boom, right about there. So 5.26 seconds or so it's showing that it would take to get across the stream. So in this situation, you have the velocity. I said, we can determine what the combined velocity is. We can think about the individual velocities. We can calculate how long it takes to reach the other bank and how far down the bank it'll reach. And we can confirm all those things based on the representation of this situation with the applet, okay? The program or whatever. So the notation that also is going to be talked about here is we want you to think of the velocity of the boat relative to the shore, right? That combined velocity that you see going on this green diagonal, right? That's the velocity of the boat relative to the shore. It is the sum of the two, right? It's the 2 velocities, the velocity of the river and the boat added up. And so how that looks is we have the velocity of the boat relative to the water, right? That's the boat's speedometer. Then you have the velocity of the water relative to the shore. So if you notice, we're starting with velocity of the boat, and we tie it together with velocities of the water in the middle, right? And then so basically it's like boat relative to shore in the end. So that's like a 2-step process. Oh no. I think we're good. Sorry, I was thinking I had something weird going on because of the smartboard frozen, but it'll be doing the screen from the computer. We're good. Mini panic attack. So velocity of boat relative to water, relative to water, relative to shore kind of thing. Means we're starting with the boat, ending with the shore. So that's how it works. So let's do the math here. So we are going to look at the velocity of the boat relative to the shore, which would just be the 2 velocities adding up. And so we're going to have that velocity, I think it was blue on this applet here, so I'll use that, is the 6 meters per second. And again, this is the velocity of like the boat relative to the shore, if you want to, or relative to the water, sorry. I'll just do VB relative to water. Then we have a red version here of the river, which was 3, so velocity of the river or the water relative to the shore. And so we're getting this green diagonal, this, right? This is the velocity of the boat relative to the shore. Okay, so obviously we don't have to worry about components and so on as much here. We can just literally just calculate this directly because of the easy math of it being a right triangle directly. So we could just cut right to root of the 6 squared less the 3 squared. It's going to give us, what, 6 squared plus 3 squared is 36 plus 9. And we get that, so we're going to root it. And so we get root of 45 is 6.7 or so. So we get 6.7 meters per second. And obviously, if we're saying like this is a velocity of the boat relative to the shore and so on, we kind of like to have a direction here for this, right? And so we can get that as well. Let's go purple for that one. I've got my purple handy here. Right, so that angle there, a little chubby. Let's go here. Save tool properties. All right, so here we go. Theta, and so theta equals, jumping right to tan inverse of opposite over hypotenuse. And so tan inverse of the 3 over the 6. And so tan inverse of a half. So 0.5 tan inverse. It is an angle of 26.56, so 26.6 degrees or so. So this angle here is 26.6 degrees downstream. Would be an easy way to describe it, or you could say north, north 26.6 degrees east, based on the arrangement of things here. Okay, so that's the combined velocity. So that's part A, and then the second part here, how long it would take to reach the other bank. So there's things we can do here. So the river was 30 meters across. In our example, I don't know if it was in this old one, but let's calculate how long this should take. And so we can do this multiple ways. So let's do it the way we're talking about here. If we want to know a displacement in the vertical direction, we're just going to worry about the vertical stuff, right? So we're going to use our vertical velocity for our vertical displacement calculations. The T in the bottom, of course. So going back to our vertical, well, just the idea of it, the vertical velocity is literally just the 6. So we have 6, and we're traveling 30, and so we can solve for the time. We're just using the given component of the 6, right? Because the 6 really is the component of the overall velocity. So 6 delta t equals the 30, divide both sides by 6, and we're going to get 5, of course, right? So we get 5 seconds to go across. So right away, even actually looking at it, when I did the app, it was around 5 seconds. It was 5.26 seconds, depending on start times and or reaction times and so on. So you can see that's pretty darn close to matching what it should be. I would trust the 5 seconds more than my clicking of the mouse. Yeah, I think that's all I want to say there for that for now, because I think I have another page dedicated to the rest. So how far down the bank will it land? In other words, we're talking about a delta dx. Well, what matters for delta dx? Velocity in the x direction, right? So we have velocity in the x direction, displacement in the x direction over time. And so we have the river's speed is the 3, delta dx, and our time of the 5 seconds. So we look at the delta dx, multiply both sides by 5, and we get 15. Again, go back to the app and look and see where it landed, and right around that 15 mark that it's supposed to be. All right. Try to point to it at the smartboard here, but you're not seeing my hand. So right around that 15, of course. So everything's matching and making sense. And you can even confirm the combined velocity. So the total velocity we said was, remind me here, 6.7 or so. So 6.7 meters per second at 26.6 degrees downstream. Well, what's the displacement overall? I don't think we'd calculated that one yet, actually. So we have a calculation to do for that one first, I suppose. We know that this was 30, and then this was 15. And so delta D equals the root of the 30 squared plus the 15 squared. Calculate that. $30 squared plus 15 squared equals that, and we're going to root that thing. Gives us 33.54, or 33.5 roughly anyways. So there we go, 33.5 meters, and usual stuff, right? What's our time? And so we're going to use velocity equals displacement over time and see what we get. So velocity was the 6.7, displacement diagonally is 33.5, and so we should get a time similar to, or really close to that 5 seconds, right? So let's calculate that out, see what we get. So 33.5 divided by that 6.7. Now I've rounded a lot in both cases, but man, that actually worked out better than I thought it would. So 5 seconds. So this is confirming those are victory slashes. I think I've mentioned that before, right? So you can see that the combined velocity of the river and the boat, works properly with the combined displacements and so on. So a lot of people get mixed up, or they're worried about doing this calculation because it's not just going vertically, right? People say, oh, but it's going diagonally. Yeah, but as it's going diagonally, it's going vertically at a certain rate and traveling a certain displacement. And it's also traveling horizontally at a certain rate and traveling a certain displacement. They all make sense. So even though this combined velocity is what you see, everything all still makes sense. Okay? The thinking questions beyond this would be for you to try to think about what way the boat would have to aim to get across as fast as possible. So have that time, this 5 seconds, be as short as possible. Maybe this is the direction, maybe it isn't. What's the fastest time that it can get across, and which way do you aim? And then the other one is, which way should you aim to end up going straight across instead of getting swept downstream? Okay, so either question that maybe they're the same as each other, maybe they're not, or whatever, but those are some thinking questions that are a bit of a challenge typically. So that's it for this lesson. So there's some easy starting questions to do with just labeling of things, right? So this one here, obviously this ends up being the velocity of the plane relative to the ground. So it's plane relative to air, and then air relative to the ground. So connect the first one and the last one. So I did the first one with you here. This one's the opposite, where we want to know the velocity of a person walking in a train. What's the velocity relative to the ground overall? So break it down like this. I think this is, I'm not expecting a long answer here, but obviously, velocities combine and calculations are possible to do. Basic question here of just getting the component, and yeah, I think they're all pretty good. This one's a lot more like what we did in class, that we get the river and so on. So how long does it take to cross the river? What's the combined velocity, and so on and so on, just like we did. And then this thinking question built in here for you. Okay, go straight across, and I should add on and direction to get across as quickly as possible. So both versions of the extra thinking question idea, we'll be taking that stuff up soon enough. But I mean, you're going to have a chance to see if your intuition is correct or not. Think about it. And the last one's similar idea. Yeah. All right. So there you go. All for now.